run all the simulations. I'm gonna upload it to YouTube right after that. So when you guys are working on it, you can open up the link and look at it. So I'm gonna go through it pretty. I won't do it very slow because I'm recording it. It's okay if you miss anything, don't understand right now. It's okay. So you'll have the time to review it. So LTSPICE you can download. It's free, and you can download it to your laptop. If you have one, but I think the desktop has LTSPICE in there as well. I'll just type LTSPICE, and you don't have to follow me. All right. I prefer that you just listen to me, but not following making the circuits, because you couldn't follow. It's gonna be fast. So I open it up, and I'm gonna create a new schematic by clicking this button. So new schematic, and F2 is gonna bring up the library. It has all the components, right? I'm gonna move it to the right hand side. It's a voltage here. That's just a voltage source, and I pressed escape, so I canceled it. I shouldn't, right? F2 voltage, place it, escape. And resistor, you don't have to bring it from the library. It's right here on the top. And Control R, you can rotate it. And Control R, you can rotate it back. Escape, right? And then F3 will let you connect all the components together. And left click will make the connection, right? And so in the lab menu, most of the circuits they don't have a ground, but I prefer just put a ground here in case that LTSPICE is going to report a error for some reason. It's not doing anything except for setting a 0 volts reference. Okay, let's just make a reference 0 volts, so we know that exact voltages for each node. And right click, you can change the value. Let's make 1K, for example, and 1K here as well. Right click, and let's make a 5 volts. 5 volts for the battery. And you can add a node. I'll call it VL, for example, and I put it here. So where to grab the node, which is here, this label. Click it and then name the node as VL. So this node, I think it doesn't have a name. But let's name it as VIN. I'm going to put it here. Okay. So now we can run the simulation. So for a DC circuit like that, there are a couple ways to run the simulation. So the easiest way is just do a .op. I clicked here and put a .op here. That's a SPICE code, I think, or SPICE simulation command. The .op is operating point. It's being used for transistors operating point, but it's being used here as well, even though we are not running an operating point. For a DC circuit, it's just gonna give you a report showing you all the voltages at each node and all the static currents running through the resistors. And you won't see any waveforms by running .op simulation. Okay, I just put a .op here and run. Okay, so you are not seeing any waveforms. It just shows you 5 volts for VIN, and it's a voltage divider. That's why you are getting 2.5 volts for the VL. And also the currents flow through every single resistor. Okay, and you can do another type of simulation. I want to see a waveform, like you probe your circuit using an oscilloscope. And it's a time domain plot, because oscilloscope, the x-axis of the oscilloscope is time, and the y is voltage. So I can delete it. Then I'm going to run the transient analysis. It's .tran, .tran, and you can run from 0 second to like 1 second. And the resolution for each point is, for example, 1 millisecond is 1 m, is 1 millisecond for each plot, each dot in the plot. And that's a formal way to do it, but usually I never did that. A lot of times I just put a transient analysis at 1. So it's going to stop at 1 second. It's going to start plotting anything from 0 second and will stop at 1 second. You know what I mean? But you should understand that if you see like 0 to 1 and the resolution is like 0.1 millisecond, you know what that means. But I just don't do that, okay? Just make it easier and faster. Okay, I'm going to run it, and now we got a like something looks very similar to the oscilloscope. It's time domain plot, and you haven't seen anything here yet. So you can probe it. See, left click. So you can plot V out, which is DC voltage, like 2.5 volts, and you can plot V in. It's going to show it here is 5 volts DC voltage. And you can even plot the currents by putting your mouse in the middle of the component. You can see it's pointing up, like a current meter, but it's pointing up, which means the current is being measured as from bottom to top, right? It's flowing up. That's very interesting. Right? The resistors have a polarity. Resistors do not have polarity, right? But in LTSPICE, these resistors do have a difference for the two terminals. If I just place the resistor here like this, and you can see the current by default is flowing up. So if I plot it, I'm getting a minus 2.5 milliamp. There's no way to get a plus 2.5 milliamp. Because you can see that here has V in is an input voltage, has a higher potential, so it's pushing the charges back to the cathode. So you're actually getting a current flowing from top to the bottom. But by default, the LTSPICE resistor is not plotting the current in the way you desire. But you can change it. Okay, so you can use this hand tool here and take it out. Keep in mind, you got two hand tools. This hand tool is going to cut the component from the circuit, and you can move it around. But this one will not cut it. It's still here. Okay? But now I want to cut it because I want to rotate it. Control R, Control R. All right, and then I'm going to run it again. So you can see it's pointing down. So it's very interesting that resistors in LTSPICE has polarity, but not really polarity, but they do have a difference between the two terminals. If you want to probe the current in a different way, make sure you rotate it. Okay, so now I'm getting 2.5 milliamp. Right, and there's another. So there are a couple of different simulation types. I just showed you .op and .tran, transient analysis, and also .dc. So it's a DC analysis, or it's called a DC sweep. Keep in mind, DC sweep, because I'm sweeping the voltage input of V1. So it's going to be .dc, and I'm picking up V1. And V1, I want to sweep it from 0 to 10 volts. Okay, and each 1 volt, I'm going to plot, like make it smaller. 0.1 volt, I'm going to plot a dot in the waveform. Okay, so this is called the DC sweep or DC analysis. .dc, the source you want to sweep, and starting voltage, end voltage, and 0.1 is a resolution. So now keep in mind, I got a 5 volt set up for this voltage source, and now I'm doing a sweep. Is there any conflict? So it's not 5 volts anymore. I'm sweeping it from 0 to 10. Do I need to fix anything? Do I need to change anything here? Keep in mind, in DC sweep, in LTSPICE, you don't, right? So doesn't matter it's 5 volts, doesn't matter it's 1,000 volts, it doesn't matter at all, or 0 volts, because this one is going to override it. The DC sweep from 0 to 10 volts is going to sweep it, right? So this voltage will be ignored by LTSPICE when it runs the simulation. So right now I just set it as 0 volts, right? I'm going to run DC sweep, and I can see that I want to probe, for example, V in. I just double click it. Keep in mind, if you double click that voltage or the node, you are going to just show that parameter in the plotting instead of a lot of other things. Because right now I double clicked the V in, so I deleted all the other things to be plotted in this figure. And if I single click V out, you can see they are being plotted in the waveform at the same time. But now I don't want to see V in anymore. I just double click V out. So V out will be there by itself. And now I want to show V in again, right? So you can see that the x-axis is V in. And for the black one, let's just plot V in, okay? In this plot, The x-axis is V in because I sweep it from 0 to 10 volts. It makes sense from 0 to 10 volts. And what is the y-axis? Mm. Mm. But what is that? What is that plot? What is it plotting right now? The x-axis is V in because I'm sweeping V in. So what is y? No, it's still V in. See, I plotted V in. Do you see V in here? I probed V in. That's why I'm plotting V in. But I'm also sweeping V in. So that's why V in is 0 to 10 volts. And y is also 0 to 10 volts. So what's the function for this plot? Yeah. Make sense? And now I'm plotting V out. So I'm sweeping V in, but the y-axis right now is V out, right? But is the V out in this form making sense? It's just half of V in, right? It's a voltage divider, so it's just 50% of the V in. That's DC sweep. And we can change that source, for example, to AC signal like sine wave. We can put a sine wave in the voltage symbol. DC offside 0 also swing around 0 volts. Amplitude like 5 volts. Frequency 5K hertz. Okay, so I can make a sine wave. And now, can I still sweep it? Maybe, but I don't want to do that because I just want to see the sine wave. So when you plot a sine wave, what is the x-axis? Time. I show the sine wave on the oscilloscope. So the x-axis must be time. So you need which kind of analysis? DC sweep or DC sweep? The x-axis is what? Voltage. Yes, there's AC sweep. AC sweep is for a body plot. It's probably we're not covering that today. So just AC sweep. We are doing an AC signal, but we want to run it and want to see it, see the sine wave. So the type of simulation should be transient analysis, like the DC voltage I just showed you guys should be dot tran. Sinusoidal is the voltage source, but we are doing an analysis like the way we want to see it, right? That's a SPICE simulation code, which is a transient analysis, dot tran, and you have to look at the frequency of the sine wave. So, for example, I want to do a 1 second simulation. What's going to happen? The sine wave is at 5K hertz. I want to run the 1 second simulation. What's going to happen? Yeah, it's going to be like a solid like plot, right? There's just so many sine waves in there squeezed together. So don't want to do that. So whenever you are doing a timing domain analysis for a frequency, for alternating voltage, you have to look at the frequency first. So for 5 kilohertz, maybe just show like 10 periods in the plot will be reasonable. So 5 kilohertz, what's the period? Like 0.2 millisecond, right? If we plot like 1 millisecond, 1 amp, I'm going to show like 5 periods in there, so it's reasonable. I'll see 5 periods of sine wave forms. Okay. Okay. So that's a transient analysis for sine wave. And this is just one way to do it, but also you can write a SPICE code for this circuit instead of dragging and drop all the components. We show how to do it. Okay. So LTSPICE right now is open. Just forget about everything I just did for you. Right now I have to start over from a new circuit. So the way to do that is you have to create a text editor file, and let's call it just test. Okay. You don't have to change the extension. Just keep it text and open it up. And the first line is a comment or title. So let's just call it example 1. Okay. And for the circuit here, I write delete. No, I didn't. Let me show you this one instead. Okay, let's look at the first one. So like this circuit, before you start writing the SPICE code, you have to label the nodes first. And this is 0, right? Since I grounded, I just labeled as 0. And this is 1, I just label as 1 and 2. I only have 3 nodes in this circuit. So when I write the SPICE code for it, here I'm showing you how to write it up. Start with the voltage, like V1. So V1 can be, you just have to start with V. It can be V1, can be VR, can be whatever V, right? This has to start with V. So the SPICE software can recognize the voltage source. I just call it V1. And V1, you have to, the nodes has to follow the order from anode to cathode. So it's going to be 1 to 0, right? That's a voltage drop. And from 1 to 0, it drops like 5 volts, for example. Okay, and then R1, it doesn't matter it's R1 or whatever, right? It doesn't matter it's lowercase, uppercase, can be lowercase R1, can be uppercase R1, doesn't matter. But it has to start with R. So LTSPICE can recognize the resistor component. So R1 is from where to where? 1 to 2, right? And it's 1K ohms, for example. And R2 is from 2 to 0. So that's how you make the circuit. It just comes back. So voltage drops from 1 to 0 and resistors from 1 to 2 and this resistor from 2 to 0. So this is the entire circuit. And then you have to type the simulation code here. For example, we are doing a transient analysis for 1 second, right? And just save it. That's everything about the SPICE code. Okay, and I'm done with it. So I just open it up from here, open, and find it from the desktop. You couldn't see it because it didn't show all the format or the file types, just all files. So you can see this text editor file and open it up. And then now you can see that it shows up in your LTSPICE window. And this is your circuit. It's ready to simulation for the simulation because you have the simulation code here. Let's just run the simulation. Oh, missing resistance value. Yeah. Let's put a 1K here and run it. Okay. And how to probe it? There's no circuit to probe. Couldn't click. So right click at the window, right click, and go to add traces. You can add V1, V2, right? So it's going to show you V1, V2, which is 5 volts and 2.5 volts. And also you can add more plot planes. And you can drag it. Okay, and you can add more if you like, if you have more signals. You can do this. You can delete it, just press delete on your keyboard and delete it. And you can delete the plot pin as well. Okay. So you just need to learn the 2 ways to build a circuit in LTSPICE. The first way is use the symbols and the graphic user interface, or you can use the SPICE code. So SPICE stands for what? I wouldn't put in the quiz since my professor treated me emphasis. Yeah, it's simulation programmer. Oh, simulation program, right? Simulation program with the integrated circuit emphasis. So with the integrated circuit emphasis, which means you can build integrated circuits in here. And it's not just getting blocks for you guys, like other simulation tools that I rarely use, right? Because if I want to build something, I just grab a breadboard and plug in the chips onto the board and run the testing. So for integrated circuit, it's difficult because they're tiny. You couldn't do it yourself a lot of times. So that's why, in F2, you can see all the transistors. If you take analog circuits and digital circuits in the future, you will be able to do a lot of these things. You can build a logic gates or build a CPU, all of it. Okay. Yeah.
Make sure you don't get overcurrent.
Yeah, definitely. The simulation is very important that before you send it out for fabrication. So the cheapest one, usually for the company like Apple or Samsung, when they are prototyping their chips, their CPUs, the fees, the prototyping fees just for one design sometimes can be from $500,000 to $1 million for the most modern technology. For example, the like 5 nanometer technology, if they send it to TSMC, Taiwan Semiconductor Manufacturing Company, for prototyping, like only 20 copies, 100 copies for the 5 nanometer technology, it can be $500,000 to $1 million. I don't know. And it's a one-time piece. It's just very expensive to run the process. And yeah, it's a one-time piece. If it's verified, you can just fabricate like 2 million of them and sell them, so you can bring the cost down to like only $10. So that's the way they do it. But we have the chance to manufacture IC chip. Luckily, you guys have, but not other college kids in this country. So only five or four colleges in the country are doing this for undergraduates, and we're one of them. So for integrated circuit design, if you take my senior son and take my 338 class, you'll be able to do it. And we have not 5 nanometer technology, but 180 nanometer technology, which is still very popular. And the prototyping, we call tape out, the fee that we pay to a third party company to collect all the designs is $6,000 for one design. The students on the team, they can have it come up with one design and we send it out. And I have a wire bonder. Students can receive the chip and bond it on the IC package and test it. So it's a fantastic opportunity for you guys. Hopefully you guys can have the chance to do it. These ones are, I think I already showed you the AC signal, how to add a sine wave to it. These are trivial, I think. It's just more resistors. And when you have to deal with a dependent source, it can be a little bit complicated. But this one doesn't have a dependent source. So this is a current source. I'm going to show you where's the current source. Again, it's recorded, right? You don't have to worry about it. So the current source is this one. It's a just DC current source. And you can see that this is a dependent source. I don't know. I mean, but when I was in college, I didn't understand what's going on, but now it's easy. I don't know if you guys are in the same situation, but it's just a dependent source. You don't have to think about very deep. Like I never seen a dependent source anywhere. Like, is it a dependent source? No, I've never seen that, but it's just happening, right? So when you get into analog circuits, you'll learn why we have dependent sources, because these are all the transistor models. But for now, we don't have to worry about that. Just look at if you have an arrow in the symbol, which means there's a current source to show a current. If you have a plus minus, it's a voltage source showing the polarities and voltage drops. So there's potential differences. But if you see an arrow in the symbol, it's a current source, and it's a voltage dependent current source because the current value is a current source, right? And it has to have a current value. So what's the current is providing to the circuit? So the current value equals V divided by 750. It's just a number. So what is this V? Where is this delta V? It's over here. It's very interesting. So the voltage across this resistor will control the current output. Okay, and we assume everything is constant, right? So it's not changing. So whatever the voltage across the resistor is, it's gonna give you a certain current value for here. So we are using amps and voltages, keep in mind, as a standard unit. So for example, this voltage is 1 volt. So we want to use 1 over 750, and the result will be amps, will be amps. Keep in mind, you don't want to say, hey, I got a 1 volt here, and I have to convert it into 1,000 millivolts, and I put it here, so I'm getting, yeah, you're getting like 1,000 over 750 milliamps, which is fine, but we just use standard units to not confusing ourselves. Volts and ampere, okay? So how do we make a current voltage control current source? Voltage control current source. F2, right? See? You got a G and G2. Let's just use G. And for example, let me try. You got a voltage, three resistors. Okay, let's do it. Grab a voltage, just constant voltage source, and I got a there's one here, one in the middle, and two on the top. Here, here. F3 will make the connections. I think there's another resistor here. So LTSPICE is not just for completing the homework assignments and for teaching, right? So when I design I can give an example. That was last year, October, I guess. The company just reached out to me, wanted me to design a high voltage generator for them because the high voltage can clean up the air. I don't know if you have seen that. It's really magical. You turn on the high voltage source, and then it has a little very sharp tip in the front. And that sharp tip is going to generate a lot of ions. It's going to ionize the air. So generate a lot of tons of positive and negative ions. And these ions will attach to the particles, the dust particles in the room, and make them heavier. So they will just get down to the surface or the floor or a table surface and clean up the air. So it's not just an academic project. It's being used for a few companies that they are selling the components to the shopping malls, to the factories. They put it in the HVAC system to clean up the air. It's already working. And they want to make one for Tesla and want to promote it as a technology to a different company. Hopefully can be used. We patented that last year. So for that type of project, I'm designing a high voltage switch because I still don't know how to do it. I have never done that before. So I have to test a lot of ideas really quickly. So LTSPICE is the only option I can use. I have to build all the transistor circuit in there and test if I can get that high voltage being oscillated. But eventually, none of the ideas work. But I got another idea, and we patented a couple months ago. But anyway, if I don't try LTSPICE, I have to spend another couple months just building on the breadboard and test it out. But LTSPICE can give me a really fast result based on any ideas I have at the very beginning of the design. But in the future, after I finalize the design, I'm not going to use LTSPICE to design the PCB board or to fabricate anything. It's for simulation. So the PCB design tools, the software is something else. It's being covered in microcontrollers 351, that class. Or this class, actually, in the very last lab, you're going to make a little PCB board for the robot. But they are all different tools you use for different stages of the project. Now let's make the connections. I'll tell you how to make this voltage. Oh, what is this? What's the name of the source again? Just to remember. We got 4 different types of dependent sources. Dependent sources or independent sources? Yeah. 4, right? Yeah. What is this one? G means it's a gain here. So if I label this guy as A, all right, so I'm gonna duplicate that. I'm gonna short it here. So keep in mind, in LTSPICE, you don't have to physically wire them together. If you label them the same name, they're the same node. they are physically shorted behind the scene. Okay, I got an A here, I got an A here, they are shorted. What about this one? I just ground it. No issues, right? So I got a reference. So VA will be the voltage input, like voltage control current source, right? So that's the voltage input. And gain, right? If you look at the here, what's the gain? So it's V. So this plot or this drawing is not the LTSPICE schematic drawing, keep in mind. You don't want to put a V over 750. It's not working that way. So LTSPICE, you already chose the voltage control current source. So LTSPICE knows that it's going to be the current value is going to be this gain times VA. So just need to set up a gain here. So what is that gain? The 1 over 750? You just couldn't use it here. You have to calculate it first, get a fractional number. So 1 over 750 is, I tried, it didn't work. I think it's because it's yeah, I think so. Only rational, I guess. So it's going to be a 0.013, if I'm right. Oh, 0013. And are we ready? Not ready yet, right? And the values for the resistors. 5, 2K, 1K. $500, 2K, 1K. I'll just pick up these values. Doesn't matter if they're not accurate. 200, 50 volts. Okay. You can label this point if you like. Let's label that as B, for example. Anything else you want to run a simulation? What type of simulation you want to run, right? You want to tell LTSPICE. Let's just run it's a DC circuit. You can run either .op, right? No problem. So it's going to show a table. Or you can do a transient analysis for 1 second, right? And run it. It's going to be an oscilloscope view. You can probe the current, you can probe the voltage, whatever you want to do, okay? Any questions on this? Right. Let's look at another example. This is a current-dependent voltage source. Current-dependent voltage source. Let me show you how to do it. So current-dependent voltage source, for example, this one, right? This is this the same as? Let me just make it smaller. So I don't have to switch in between these two. Okay. So this schematic is here, but you can see I have a extra voltage source over here, because when you have to do a current-dependent, current-controlled voltage source like this one, you have to have a dummy voltage source here, but set at 0 volts. So it's able to find the current flows through this voltage source. I just have to follow it. There's no like why it has to be that. Like, whoever designed LTSPICE, they made it that way. Because I'm trying to use the current flow through this resistor, right? You can see I put this dummy voltage source in the same branch as the resistor, so they have the same current. But however, I don't want to affect the circuit at all, so I'm just using a 0 volts. So it's not dropping any voltage. Okay, just like a wire. But the voltage source, the ideal voltage source here is able to sense that current. So I have to put it here, like V3. So setting V3 is current flowing from plus to minus. Keep in mind, whenever you use this dummy voltage source, it has to flow from plus to minus because the current pointed from right to left, right, in the circuit. So I have to use the current in that way as a controlled current.
So that's just like programming.
Yeah, that's right. Yeah. There's nothing about modeling.
So if you have a voltage source, so you define it.
That's right. Yeah, if you place your dummy voltage source that way, it's going to create a current from right to left. If you rotate it, it's going to be the other way. Keep in mind. So if I put it this way, it's going to sense a current from right to left or from the plus to minus in that direction internally. And then I'm going to grab a H1, keep in mind, find out H, this guy. So this is a current dependent, current control voltage source. You have to use H here and do not change H1, okay? Change the V, if I grab one, for example, H. You are not changing H1 and H2, these are just names. But you are changing H, which is the value. So H is V3. It's better to right click it, right click. So you can change value to be V3 and value 2 to be 6.25, which is the gain here. Make sense? Now know how to make it. Okay, grab a H, okay, and right click, change value and value 2 accordingly, and put a dummy source here in the right direction. That's it. Current controlled voltage source. Okay. Here, voltage controlled current source. Is that the same? Same. Same thing, okay? It's not changing anything. And that's it. So in the future, please, I'm sorry for the confusing guys last night because I didn't specify the requirements for the lab reports, but in the future, just follow whatever in the lab instructions. If he says, just answer questions, don't have to follow all the sections like introduction, materials, and results. Just don't do that. Okay, just follow whatever is being specified in the lab instructions. And I think the only difference between our section and the section 1 was like we were able to get all the labs done, but they didn't. That's the only difference. Just to follow the same format, but just plug in your results in there and submit it. And when I was teaching the class, I let every single student to have generate their own reports, like individual reports, not the group reports. But I think for section 1, I think they are doing a group reports, I guess. Did Dr. Justin tell you guys, like, should be group reports instead of individual ones, right? Okay, yeah, then just do group reports. I'm fine with it. Just make sure you contribute to the project, not just someone just sitting, right? You're just kind of watching, right? I get popcorns and you'll do it. I'm just resting. No lab reports, but you need simulation results, right? You have to answer the questions. Yeah, I have to do it. Yeah. Screenshot.